Let me put 15 minutes that we have to good use. And let me show you some of the preludes of dynamics. I'm going to go back to the case of 1A1Z. So, and you saw that 1A1Z, you can calculate the structures fairly straightforward. It's not a big deal. This particular instance of 1A1Z, I have subjected 1A1Z to two-state jump motion, where a portion of the protein is jumping between state 1 and state 2. And I have created residual dipolar couplings from that averaged RDC. Now, the question becomes, how would dynamics manifest itself in our studies? So I'll show you that quickly in the next 10, 15 minutes. And from that point forward, we can adjourn, or if there are additional questions, we can answer. So 1A1Z, I showed that you needed to have Ramachandran level 2 to be successful. So here I will do the same thing. Then I showed that if you go to, I'm going to leave everything here as is to demonstrate what happens. Let me further reduce this to 500. And if I go to basic and just basically run everything as is, with this exact setting, I was able to fold 1A1Z under the conditions of being static structure. Here, I'm going to run it. This may take a little bit. So in the meanwhile, somebody's knocking on my door. I'm sorry. I'm going to go see who it is. I'll be right back. Let me know if you have success on I can implement it on the other. Bye. Okay, so yeah, you can see that it is actually it's more taxing. It's calculating stuff. It's part of it is because I do not have J couplings, and therefore in this particular data set, so it's more extensive calculation. I can study the health of my folding at this point by looking at the latest .out file. And you can see that at this point, I am seeing the typical, what we call dynamic profile, where the best structures that I see across as the fragment is elongated is illustrated in red. So gradual increase with platforming and plateauing at error levels that are below my expected experimental error. So that looks good. I can maybe go further. So let me look at the structure 25.pdb. What does it look like compared to 1A1Z actual structure? And at this point, I'm 0.8 angstroms away. So here I'm folding 1A1Z with only 4 RDCs per alignment medium. You can see that I started with poorly populated sparse data. So what would have been better is that if I had started my structure calculation maybe from residue number 4 onward. But in this particular case, you know, it works. It works fine.
Home, probably you already mentioned this. So, is there like a percentage for depending on the number of residues? Or you said like two RDCs per residue is the
Right.
average
So
you
this
need?
becomes another advantage of RDC approach versus NOE approach. If I was to ask a person, um, an NMR expert, say, how many NOEs do you need in order to unambiguously, theoretically, to be complete in structure calculation? That answer is unknown.
Right.
You can say anecdotally, you kind of need to have 15-ish NOEs per residue
Per residue, yeah.
successful. Fine, but for regions where you have less than 15, then the implication of ambiguity in structure calculation will become uncertain. So if you drop for some region, for some residue from 15 to 10, what is the impact of that in your quality of structure? And if your structure is then poorly defined there, is it going to be mistaken for dynamics? It's just the issue gets clouded.
Right.
This particular approach that I'm presenting to you, the connectivity between residue I and residue I plus 1, or peptide plane I and I plus 1, is governed by only two variables, phi and psi. Because my variability of space is only two variables, therefore, in theory, I only need to have two pieces of data in order to remain deterministic. Less than two makes your problem to be underdetermined. More than two makes your problem to be overdetermined and desirable. So I can tell you, in theory, you need to have two independent pieces of data per residue in order to be theoretically sound in structure calculation. So that's based on theory. In practice, the question becomes, is your search algorithm comprehensive enough to find the global optimal point
Correct.
and not get trapped in your local minima?
Exactly.
And so then now you will be limited based on the pragmatics of your algorithm, which for Redcraft, based on our approach, what we have seen, if you have two RDCs in tool media, you're successful as long as the two RDCs, one of them is an H, and then, the second piece, of course, C alpha, H alpha is most complementary, but it may not fit your data. For example, you may have a deuterated protein, which then everything that you want to collect is going to be with amide proton.
Right.
So NH, carbonyl nitrogen, carbonyl amide proton, all of those will work fine. So yeah, so I can with some degree of certainty say two RDCs will work for you.
So with this Redcraft's approach, therefore, there is no business of this cluster of structures within this window of so many angstrom variation, right? Where like we do with NOE, only NOE based structure calculations. So you kind of, it looks like all your PDB files, you just showed just the final structure.
Right.
One.
Right, and the recognition there is that first, you never have just a single PDB. You always have a structure such that the alteration of that structure still fits your within data.
Okay.
Now, what we have done in the past, when we when we deposit structures to PDB says, no, you need to give us an ensemble since it's an NMR method.
Yeah.
Then what we do, so like for example, at 52, we have a single PDB, but that single PDB corresponds to this first line.
Okay, I see.
So what we do then, we create a structure from the first 10 or 20, and here are all the structures that are within some X variation. So at that point, RDC fitness varies anywhere from 0.32 to 0.33. So we just provide that.
Oh, I see. I see. Okay, it's there. But the only thing is,
it's
yeah.
There. It's just that if you want to look at the best structure, well, that best structure is 53.pdb.
Okay.
So we are getting at the point that things are being interesting. So let me look at 55 that out. And you can see that still I am exhibiting the same performance of monotonic increasing, plateauing, but it seems like there's this dip now.
Yeah.
So let's see where that goes. That could be a variety of things. So let's see what 57 that out looks like. So 57 that out corresponds, it seems like it's still going up. And I'm going to wait for this to go on until 60-ish, 60, maybe 1, 2. And at that point, I think the point will become clear. This is 59 that out. The pattern still continues. There is some sort of a disagreement is taking place.
So, Homi, while we're waiting, can I ask one more hypothetical question?
No problem.
So if I had, let us say for a structure, if there's an infrequent exchange problem where I have two peaks, which 100% I don't know, let's say I've assigned pretty much every one of them, there's an extra peak, I'm kind of scratching my head. Will this dynamics-based approach shed some light saying there is some exchange going on at that part?
So
By
the
this
exchange, is it by exchange, I presume
chemical
it
exchange?
implies that you're at some sort of a time observable time scale,
Yeah.
your structure is existing in two potential states.
Correct. Yeah, that's right. A part of it, a part of that. Let's say like a localized vibration, or libration, or motion, or something. Yeah.
Right. So it depends on how that reflects itself on your spectra. If you observe an averaged RDC,
Yeah.
if you see an averaged RDC, that's exactly what's going to appear like here.
Correct.
All right. So you're going to see, and so you're going to observe. Let me. So then jump into this topic. So at this point, what you're going to see is this, that you can see that it is increasing and then it plateaus.
Exactly.
Now,
I
I
was
have
coming
worked
to.
with this phenomenon long enough, and it adheres to theory perfectly. So the violation that's being observed here is that either Ramachandran space was too constrained.
Yeah.
My assumptions about the rigidity or about the peptide plane is violated,
Right.
or it is dynamic. The first one, whether it's a localized Ramachandran, constrained Ramachandran, or whether my cis-trans, amino acid would appear as a blip followed by a return back to the plateau behavior.
Oh, okay. As you go along the chain, I see.
Exactly. Whereas here, it just continuously shows discrepancy, and that discrepancy it plateaus, but it continues.
Yeah.
This is an indication of dynamics.
Wow.
And at this point, the question is it dynamics? What is the magnitude of dynamics? And what is the mode of dynamics? And in one of our most recent publications, we try to decipher or classify modes of dynamics. Mode of dynamic can be, are you a rigid body dynamics, or are you uncorrelated dynamics, meaning from residue, whatever it is, 50 some on thing onward, is the protein melting?
Yeah.
Or is it a hinge behavior that there is this segment of the protein that may act as a hinge, and this portion, residue 65 onward, is rigid, but it is
Right.
undergoing dynamics with respect to the first domain of the protein?
Yeah.
You can
Exactly.
answer that question by the following exercise. We are kind of going into so the start of dynamic was 50 something. So here I'm going to say, I'm going to start from residue 62 and onward. I'm going to calculate my structure again.
Okay.
And so right now, structure 62, 63, 64 is being replaced here. So if I look at, like, for example, 67, first look at the output. The output
Oh,
shows the typical, that's here, by the way, it's starting at 60, whatever, it shows that incrementally going up. If you look at it further, you'll see that it exhibits the same pattern of the monotonically increasing and then plateauing. So I'm at 78 now, so let's look at 72. So you can see that it plateaued here,
right.
indicating you're getting a structure. And the question is, am I getting a good structure? So 73.pdb, this is the structure that you would, so your rigid, this portion is undergoing rigid body dynamics with respect to the first domain.
Okay,
It's a rigid because it contains this very nicely decipherable structure.
correct.
Now the question becomes, is it the magnitude of dynamics? And again, if you look at some of our work, based on ordered tensor discrepancies between two domains that are undergoing dynamics, we can reconstruct to atomic resolution to within 1 or 2 angstrom, the 2, 3, or 4 states that are consisting of the jump states.
Oh,
So if you haven't seen our publication, I recommend you look at it. And again, if anybody's interested in seeing a dynamic version of this one, where we start with structure calculation and quickly, maybe in a more timely fashion, we can talk about the principles of dynamics and how we should decipher, how we should reconstruct things.
that
So
would be
I'm going to stop at this point. This is about the time that we had planned. And between now and the next 15, 20 minutes, if there are questions, demos, requests, I'm more than happy to accommodate. Otherwise, this will be the end of this particular meeting.
I have a question about when you referred to the underdetermined problem.
Can you repeat the last part of your question? When we are what?
You were referring to the, if I heard you correctly, the number of RDCs per residue that are required to have a determined, an
Right.
overdetermined, and an
Yes.
underdetermined problem. So the minimum is 2 RDCs, otherwise it's undetermined, correct?
It's sort of, yes. It is not to take that, meaning that if you have less than 2 RDCs, in some instances, all right, if you have just 1 RDC per residue consistently throughout your protein, then you are theoretically at this point not able to calculate a structure. Although I personally argue against it, and I don't want to complicate the issue, so for now I'm just going to agree to that. But if you have a protein that you have 2 residual dipolar couplings per residue, and sporadically you have regions that you have less. So let's say you have a fragment of 10 residues with 2 RDCs per residue, and then there are 2 or 3 consecutive residues that dip into 1 or maybe even no residual dipolar couplings per residue. And then from there, you emerge back in a fragment that you have 2 RDCs consistently for another 10 residues. Redcraft can still calculate the structure of the region that dips below 2 RDCs per residue.
Okay. If I use NOEs and dipolar couplings in the way you suggested much earlier in your presentation, could we use just 1 dipolar coupling for the refinement if we started with NOEs?
So it's you are really pushing the boundaries, but it's still possible. It all depending on what is your search space. So if your search space is confined to secondary structural elements. So for example, if you have, again, in my previous example, if you have a fragment, if you have 1 residual dipolar couplings, but for a fragment of 10 residues that are clearly defined to be in a helical space, followed by loop region, followed by another helical region that has residual dipolar couplings, but only one RDC per alignment medium, then my recommendation would be to approach, you can do this, you can approach the structure calculation part of it in a more fragmented way. So first calculate the structure of the fragment 1, optimize that, calculate the structure of fragment 2, optimize it, orient the two fragments with respect to each other. And if you have in your connecting loop region that connects from fragment 1 to fragment 2, if you have residual dipolar couplings, great. You can refine the structures with respect to each other. But if you don't, then you basically, the loop region has to be defined based on the orientation of the two fragments and how they fit within the entire structure of the protein. But you can do this. It requires a little bit more of a mix and match of transitioning from Redcraft to explore to minimize, back to Redcraft to continue. But I believe it can be done.
Could you achieve that back and forth transfer by the minimization script option?
Sort of, yes. The minimization, meaning the one that I am showing here.
I think it's in your advanced option box. You have 3 check boxes,
Yeah,
and the
so,
third one is...
Right. That minimization is meant to be essentially a gradient descent based optimization purely based on residual dipolar couplings. But if you wanted to, if I understood your question properly, if you wanted to stop at some point, transfer the refinement process to, let's say, explore NIH, then at that point, your minimization routine that I had would be replaced with some sort of an explore, a conglomeration of the explore refinement procedure. And that part of it would be straightforward because at the end, Redcraft is producing PDB files. You just need to convert it to PSF, convert the RDC data to explore format, then continue refinement in explore. An explore refinement procedure will create a final PDB. To continue that in Redcraft, what you need to do, that new PDB file that comes out of explore needs to be converted back to a set of phi size and be essentially inserted in the right place in the output files of Redcraft, and then the Redcraft execution continues. So if you really wanted to automate this whole thing, you could do it that way, but you can just do it manually. For example, in here, run residue 1 through 10, get a structure, do the rest of your work in explore, get a structure, translate it back, whatever you need to do from explore to Redcraft, and then continue your Redcraft execution from 10 forward, 10 onward. By the way, so I don't know if you can see my screen, there's this continue from existing.out file. This is where you want to stop execution of Redcraft at residue 62, for example. But you want to then proceed forward continuing, not start a new run from residue 62. So you can just check this box and then do it manually. So I don't know how savvy you are in your programming skills and scripting skills. You can do that easily manually by switching back and forth between Redcraft and whatever other minimization software you have.
About scripting for Redcraft, is there a API available for Redcraft or something that we can read?
So sort of, let me show you what the minimization routine looks like. So in minimization routine, we haven't disclosed this information in a formal way, again, because the funding was discontinued. So we are happy to work with anybody who's interested to build this particular or use this particular aspect. But you basically call any script that you specify here, whether it's a Python script, Perl script, shell script, whatever script. In that script, basically, you have access to all the configuration files and all the output files of the Redcraft. and you can pass the assume execution by embedding something in here, and you can then insert things back into Redcraft, I believe, through this particular routine. But there is not a formal routine. Basically, if you maintain this part, and anything in between can be replaced by your own scripting, whether in Perl, Python, anything else, you can integrate this with Redcraft.
Okay, thank you.
You're welcome. So if there are no more questions, again, if you're, I'm more than happy to continue this conversation offline with any of you at later time. I have to go teach in about 10 minutes. We can have private sessions, we can have research collaborations, we can write grant writing. I have grants written around Redcraft that are missing my partners that say, here's protein XYZ that needs to be studied by residual dipolar couplings. So any of those, not only structure, but also dynamics.
Yeah. Homemade Jeff here.
Yeah.
First off, this has just been fantastic. So wonderful of you to take the time to do this. I'm probably speaking for everybody that it's just been really, really, really informative. And these are tools that we really need to get promulgated more widely. And hopefully the nmrbox platform can help there. But you know what? It's all the nmrbox platform is also potentially a great platform for putting together kind of a meta package, you know, that would incorporate Redcraft in a more complex workflow.
Right.
And that might be something. And I was going to, in fact, I meant to ask you, where do you stand on in terms of your seeking additional funding? Do you have anything in the pipeline, or?
Not with Redcraft at this point. I have tried a couple instances of it, and in the distant past, and it was not successful with NIH. I'm switching, potentially going to NSF because it's more technology development rather than, you know.
Right. In fact, I was going to suggest this, because this is fundamental.
Right.
So fundamental that NSF might have some interest in it.
Right.
Offline, let's have a discussion about NSF funding.
Absolutely, but I'm looking for the cost of including my work is very minimal, because it is at most is 1 month of my summer salary and one graduate student, and that's all you need. So which comes out to be very cheap. The funding that I had asked for was tie Redcraft to molecular dynamic simulation. I had suggested VMD, NAMD, but nowadays it can possibly go the route of GROMACS VMD, and on the other side to be also connected to explore NIH, which it can also go the route of GROMACS or anything else.
Sure.
To have a complete package. So what I have managed to do here, I hope that I have managed to make analysis of RDCs to be point and click kind of thing, maybe even if you don't care to know what's underneath the hood, but to connect it with other things becomes a hassle. And by asking additional funds, which is not very much, I'm hoping to make that also both opaque and transparent at the same time, to really inject it into a workflow.
Yeah. Good. Okay. Let's plan on having another maybe an offline discussion on some of these topics.
Absolutely. But if there is any interest, again, I'm itching to do dynamics, but I'll wait for the participants to actually coordinate and request that as part of the survey I believe Adam is going to send out.
Yes, Jome, I've got the survey constructed. I already put in a question specifically for that. I'll send that out to everyone as soon as we finish up here.
Okay. Thank you very much. I'm very happy to do this again. We got RedCat in line. We got Redcraft Dynamics. Any of the stuff that my lab produces, I'm more than happy to demonstrate it here online.
Fantastic. Thank you so much, Jome. This has been really helpful.
Yeah, thank you. It's by the way, nmrbox just completely rocks. Maybe that would be a T-shirt for next ENC. It's a great platform.
Cool, thanks. No, I was looking at the usage on the platform while you were doing some of your demos. Just in a moment, you would just peg 17, 18 cores and things would fly away, and then it would all subside back to background.
Yeah, it's great to have all that stuff. So. Anyways, thank you very much. It was a great pleasure. I hope everybody found this somewhat informative, but reach out and ask me questions if you got them.